All right, now with this video, we're looking at one of the most difficult, most challenging integrals you will ever encounter. This is even more challenging than the secant to the third power. It involves secant function, but to the fifth power. And this integrand that you see here, the square root of x squared plus a squared cubed, is in fact the secant function when we make the trigonometric substitution of x equals a tangent theta, and dx is a secant squared theta d theta. I did catch the fact that I didn't put the a in the original substitution. I found that, discovered it a little later, so don't worry about it. I was, in fact, cognizant of the fact that I had to have that a squared there. It's an important, it's not trivial. You can see that I put the a's in for my substitutions, and now under my square root, I've got a squared plus tangent squared theta plus a squared, now cubed, dx. But, oh, yes, don't forget the fact that dx is a secant squared theta d theta. Now, when you take a look at this, you realize that this is part of the trigonometric identity, 1 plus tangent squared theta equals secant squared theta. So we have actually in the square root a to the 6th and secant theta to the 6th power, with the a secant squared theta d theta. And now in the next line, we'll take everything out from under the square root, and we'll end up with a fifth power secant function. And what that means is we're going to have a very difficult time solving this problem. It is a very lengthy problem. I think I used two full sheets. Now, when we do this problem, we're going to use the integration by parts methodology. So we start out with trigonometric substitution, and then we choose integration by parts for the remainder of the problem. At this point, we're utilizing the fact that secant to the fifth power is equal to secant to the third times secant squared, and then we apply the 1 plus tangent squared theta equals secant squared theta identity, and break up the secant to the fifth into two terms, integrals, one with a secant to the third, secant to the third power, and the second integral is going to be a combination of secant and tangent, as you'll see here. So I'm just making that equation at this point. So at this point, we're going to apply the trigonometric identity to break the secant to the fifth power integrand into two integrals. One with secant to the third d theta, which is a problem that we solved, and the other integral with an integrand of secant to the third theta times tangent squared theta d theta. And then with the second integral, we're going to solve that first. And we're going to use integration by parts for everything from this point on. So with the both integrals, actually, the secant to the third power integral and the secant to the third tangent squared, we're going to be using integration by parts for both of those integrals. And in this, I'm choosing to solve, I believe, the second integral, the secant to the third theta tangent squared theta. And in this, I'm using a u substitution of secant theta times tangent squared theta. And there's the derivative. And I will be then finding a v, an appropriate v. And you'll see the next few steps we will, more than a few steps, we will be carrying out this through a very complicated, convoluted set of steps. As you can see, the derivative of our choice is pretty complex, and it's going to lead to multiple terms when we put them into the integral. Now, our next step is to choose a v, and here we chose tangent of theta, so dv is secant theta d theta. And now we set to the task of using integration by parts. And as we can see, we have one integral where we have what we want, which is an integrand that is secant to the third tan squared d theta. Our second integral leads us to an integrand that looks pretty nasty. At least two additional integrands that look kind of nasty. One is one we've already solved, though. So, and when you look at it, when you put it back into the equation, we end up with 3 secant to the cube terms. So when we get there, we'll identify it. Right here, we're just ordering it so that we can plug in the appropriate terms. And so we have our two terms that we bring to the left side of the equation above. We got one more term we have to write out. Okay, so now we have our So our next step, we're going to need some space to write, so we're going to use as much space as we can because we're going to be expanding the terms on the above expression. So we have secant to the third theta tan squared theta d theta equals 1/3 secant of theta tangent to the third theta d theta and in the next integral, the minus 1/3 secant theta times secant squared theta minus 1 squared, we're expanding that expression and it will give us 3 terms. And we're going to multiply that out here so that we show the full expansion of that square. And which ultimately will lead us to 3 separate integrals. But we don't take it to that step yet. We're just showing the expansion. You know that secant squared theta minus 1 squared is secant to the fourth minus 2 secant theta squared plus 1. And that's all multiplied by secant theta. That's what we're doing in this step. And we're showing the full expansion. And once we break that up into 3 integrals, I think we'll be ready then to plug it back into the original expression, which is about the 5th line down from the top. Now, because we ran out of space on the other sheet, we're going to start with a new sheet and we're going to copy down our expression that we are working on at this point, which is a to the fourth secant to the fifth theta d theta. It's a solution of that integrand. And we have a to the fourth secant to the third theta d theta, which is something that we've already solved in previous videos. And the second term, which is a to the fourth secant to the third theta d theta tangent squared theta d theta. Now, I was not careful. This is the problem in copying things over. You notice that that term is negative. I subtracted that second integral. That should be added, not subtracted. I pick up on it later. I find the mistake, but right now, please note that that's a mistake. But I do correct it. I think I referred back to the original sheet and took notice at that point that I had made a mistake in the writing of that term. So we'll see where I make notice of it, and maybe it's at this point here. Nope, I didn't. Well, I go back and I look at it. Maybe I catch it here. Yep, you see, I caught it. That's where I put the plus sign back, and now I can progress. And we can move on. Now what I do is I put in those three integrals. I don't know if I do it at this step. Maybe I write out the expanded form as a single integral, but then I ultimately have to put them into three integrals. Yeah, I think we'll see what I do in just a minute. One of the reasons why it seems like I may be taking a little time on between steps is because the television was running. I don't suggest doing these in front of a television set because it distracts your attention. But here we go. We're putting in our expression for that second term, that second integral, secant to the third theta, tangent squared theta. We're putting in that expansion. Okay, so now we're putting in that second integral. That contains the secant to the fifth, theta d theta. I think I'm adding each term independently. So I did break it up into three separate integrals, as you can notice here. You have to be really careful when you do these because it's so easy to miss something like a sign or a constant. You have to be very meticulous, otherwise you'll screw it up. And like I said, this is a particularly hard integral to solve. The secant to the fifth is not a trivial problem. It's even more challenging than the secant to the third. As you can see, it's an extraordinarily difficult, convoluted integral to solve. So now we're just doing a little cleanup work, making sure that we have all our terms written out and our signs correct and everything's in shape for us to further tackle the problem. As you can see, this is a very lengthy set of terms. Okay, we're multiplying across here. We're getting everything all cleaned up. All the integrals in their proper form. Secant to the fifth, theta d theta. Now we add our second integral. I think here I wanted to get the 2 in. 2a to the fourth, 2a to the fourth, and then the integral. I hope I have enough space because this is a very long integration. Secant to the third. You can see now we have terms that we can combine. We have a secant to the fifth and we have a secant to the third that can be combined. So it will consolidate in the end. And 3 integral of secant theta d theta. All right, now it's time for consolidating. We're going to put in the next line, we are combining the secant to the fifth terms of the equation. And if you notice here, we have a fraction, minus 1/3 a to the fourth integral secant to the fifth that can be brought to the left side of the equation. And so we end up with 4/3 a to the fourth secant to the fifth theta d theta. We also have a secant to the third theta term that can be combined. And so we do that in this next step. So we have 5/3. That's what it's going to be, 5/3 a to the fourth integral secant to the third theta d theta. So we've gone from 5 terms. Here I'm just crossing out the terms that we've dealt with. So now we have 3 terms on the right side of the equation. And lastly, our final term, which is minus a to the fourth over 3 secant theta d theta. Now, All we have to do is solve two integrals, the secant to the third integral and the secant integral, and we know how to solve both of those. So, and once we solve them, we have the whole problem solved. I'm doing one more step. I'm just cleaning up the 4/3 on the left side of the equation. So in order to clean it up into final form, I just multiply the entire right side of the equation by 3/4 and write out the terms in their final form. Just getting things ready for the final coup de grace on the integration. And essentially we have this problem solved now because we know what the solution for the secant cubed is, and we also know what the secant integral of the secant theta is. So we're just doing a little like I said, cleanup work. Oh my goodness. Because this was such a complex integral to solve, I just was taking my time. And I have this fetish for keeping things neat. You see, I have to rest my hand on the screen, and every so often it makes a little smudge, a little line. And I hate when things are cluttered up with stuff that shouldn't be there, so I take the time to erase it. Now, basically, I'm going through the solution for secant to the third theta. Just to do this correctly, I know that we've solved this before, but I want to show you again. It can't hurt. So we use integration by parts again, where we have uv, which is secant theta tan theta, equals the integral of u dv plus v du. And so that's what we're doing here. Just doing a little cleaning up here because I didn't have the correct d theta in my du. I just noticed that, so I corrected it. And now I'm writing out my last term, which should be secant to the third theta d theta. And just rearranging everything on the in its proper order. Okay, what I've done here in this line is I just kind of skipped a line because that first integral I expand the tangent squared theta using the identity secant squared theta minus 1 and then combining terms. And this way I just hastened the solution of the problem. And now I rearrange the entire problem and have the final solution for secant to the third theta d theta, which is 1/2 secant theta tan theta plus 1/2 the natural log of secant theta plus tangent theta. And of course, there's going to be, because it's an indefinite integral, it's got a constant, but we're not going to add that until we have our final solution for secant to the fifth. So now we have secant to the third term solved. And we put that back into our expression, our final expression, secant to the fifth theta d theta equals 1/2. Oh, but we have the 5/4 a to the fourth, so we have to make sure that we don't get our constants wrong, our multiplier constants. So we are taking extra precaution, taking it slowly to make sure that everything is accounted for. Again, you can really screw things up just by not getting the constants right. And now we have the two other terms. For which there isn't much room to write. I'm not sure if I go straight to the solution. We'll see in a minute for the secant theta. Now that one we've done a number of times actually. Let's see what I choose here. A to the fourth. I think I leave it in integral form and we'll see. Nope, I solve it. The solution to the secant integral of the secant theta is the natural log of secant theta plus tangent theta. So now, again, a little bit of algebraic cleaning up, but we essentially have the problem solved. We just have to make sure that all our terms are combined and our constants correct. And that's what we're doing in this next line. You notice that we're getting everything in the proper order because we've 5/4 a to the fourth times 1/2 is 5/8. Secant theta tan theta plus another 5/8 natural log of tangent theta plus secant theta or vice versa. It's all the same. And we have our last terms. A to the fourth over 4 secant theta tangent to the third theta. And we have that last term, which is the natural log, but that's subtracted from the first term. So that 5/8 actually becomes 3/8. And I think I erase the 5 here at this point and combined that first and last term in this right side of the equation. Let's just see what I do. Yep. And I added the constant just to be accurate. So now that is technically our solution to the secant to the fifth theta d theta. But now we have to put our solution back into its original terms, which were in the variable x. So what we have to do is go to another page because we just don't have the space here. Now it's a matter of putting all of this above expression back into the original variable, which is x. So we know that our first integral, a to the fourth secant to the fifth theta d theta, is the original integral, x squared plus a squared to the third dx. But we have to go back to our original trigonometric substitution and use the x equals a tangent theta, which was our original substitution. So we create a right triangle and we work out x over a is tangent theta, so the hypotenuse is the square root of x squared plus a squared. And now we're ready to put in to our equation the original variables. I have to write small because I don't have a lot of room. But that's the secant theta. The first x over a is tangent theta. And we have 3/8 a to the fourth natural log of secant theta plus tangent theta. I guess I didn't like the way I wrote the natural log. So we got the secant theta, x squared plus a squared under the square root over a plus x over a. And our final term, which we're going to be a little pressed for space, is a to the fourth over 4 we got the secant theta, which is x squared plus a squared under the square root over a, and the tangent, which is tangent cubed, which is x cubed over a cubed plus our constant. That's our solution. We have to do a little bit more cleaning up. I drew a line around the trig work in order to keep it from being confusing. And I've got some a's to cancel out and put into final form. And so we're doing that last bit of homework. Oh, geez, I forgot the dx in the integrand. Just note that I forgot in the last expression that I forgot the dx in the integrand. That's where I mean, where you have little details like that need to be addressed. And sometimes you don't notice them when you do it, and then when you come back, like I am now, to do the narration, you notice it. So everything on the right-hand side is done correctly. It's just that I screwed up the integrand of the original problem by forgetting to put the dx in. So you can mentally put that in yourself. And there we go. That's our solution there on the right-hand side. I apologize for forgetting the dx. I think I boxed the whole thing. Yep. And I still didn't notice that I forgot the dx, which is a shame. But I did get the solution. It was not an easy, as you could see, there were a lot of terms, and I was somewhat jaded by the end of this problem. That's a problem when you have such a complex, convoluted integration that you can make these mistakes pretty easily, and that's what I did. Okay, I have to fix that dx that I missed just because I want to be precise. So we make our integral, and we have Oh, let's make this neat looking. Let's make this neat looking. All right. So, our integral dx x squared plus a squared cubed. And I just want to check, make sure, whoops, that's the original integral that we were working with. Yes, indeed. That was the original integral. So we have our final solution at hand, and we box her in. I'm not being very neat about this. Okay, now let's make this as neat as possible. Okay, a little touching up here. And we have our solution. And I'm going to insert this into the video. Okay, now for our next problem, we have a similar type problem, another square root of x squared plus a squared over x. And we use again, a trigonometric substitution. And in this case, we use the trigonometric substitution a equals secant theta. So x equals secant theta, and dx equals a secant theta tan theta d theta. And the reason we use that is because in the integrand, we have a minus sign. So x squared minus a squared. It was a little hard for me to read. The resolution isn't so great in the editing form. So we have now with our trig substitution a squared secant squared theta minus a squared over a secant theta, and then we add the differential portion, which is a secant theta tan theta d theta, and then we do a little algebra to clean things up. Recognizing that in the square root, we have a squared tangent squared theta, and that's a square root, so we can pull that out. Plus we have the secant theta in the denominator and in the numerator that cancel. So we end up with an integrand of tan squared theta d theta. So we're going to use our trigonometric identities. That tangent squared theta is equal to secant squared theta minus 1. And we break the integral into 2. And now we just integrate. Very simple here because the integration of the secant squared theta is simply the trigonometric integral of tangent theta. And here I'm working out the relationship y equals tangent theta, and dy is equal to secant squared theta d theta. And if you take the integral of that, your result is the tangent theta. I'm just working it out for my own refreshment. Again, after working on that previous problem, this one seems really simple, but I still was a bit jaded from that first problem. That secant to the fifth was a bear. I would imagine any odd power of the secant is going to be a bear. So now we plug back into our original what the solution is. I elected to, okay, so I put in tangent theta minus a theta plus c, and now I have to go back to our original variable. So I make our little right triangle where x over a is the secant of theta, and we have on the vertical side of the right triangle the square root of x squared minus a squared, and we just plug in our expressions for the tangent of theta. Now I'm writing out my terms using my trigonometric identities. We have the inverse secant of x over a. And I got to remember here at this point that the constant a is missing from the second term. I forgot to put the a there. That was an oversight. And the first term, the a's cancel out. But in the second term, the a should be present in front of the arc secant. So that is a problem, but it's a minor one. But these are the little details that you need to watch out for. Now our next problem. Again, all of these problems that we're solving were taken from the chemistry, the Handbook of Physics and Chemistry. And here we have another problem that looks somewhat similar to the one we just solved, except we have the a plus sign, x squared plus a squared under the square root. So we choose a different trig substitution. X equals a tangent theta, dx equals a secant squared theta d theta, and we plug them in to our expression. So we write them into our expression. I didn't like the way that integral sign looked. So I erased it. Now I plug in. We've got a squared tangent squared theta plus a squared dx over a tangent theta Okay, and our dx term is a secant squared theta d theta. So many of these use the same approach. And now we simplify our integrand by using a little algebra. We recognize that under the square root we have a squared secant squared theta, so that when you take the square root is simply a secant theta, but we have a secant squared theta in the numerator, so we end up with secant. Well, we have a secant theta, but multiplied by secant theta. I got to get my a's straight again, which is screwy because I didn't account for the a in the denominator. I should only have one. I shouldn't have a squared in the numerator. I don't know if I catch that or not. See how simple little things can be screwed up? Yeah, I caught it. So now I got only a on the outside. So many things you have to be aware of, and you need to be careful when you do them. Now I guess I'm trying to figure out what is the best way to go, because secant to the third is secant squared times secant, and then I can use the tangent. 1 plus tangent squared equals secant squared. So I think that's the way I went. Yeah, that's exactly the way I went. And I broke up the integral into two parts. And now I do a little more algebra. Now with the secant theta tan theta, that is the derivative of the secant theta. So if u is secant theta, du is secant theta tangent theta d theta. So I use a u substitution for the second integral. So that second integral is just simply du. So I rewrite the integral, both integrals. I recognize the secant of theta is 1 over cosine, and tangent theta is sine. So I put those into terms of sine and cosine. So 1 over cosine theta, sine theta, and then I have a cosine theta in the numerator, d theta. I'm just making it neater here. Cosine theta, and then d theta. But the cosines cancel, and we have cosecant. But before I get to that point, I just recognize that the second integral is du. Now to my next line, I got cosecant plus a u plus c. And I have to do the u substitution. Well, I'm not quite ready for the substitution back into x yet, but I have to integrate the cosecant squared theta. And I do that in a similar fashion as what we do with the sine or secant of theta, by multiplying across by cosecant theta plus cotangent theta, both numerator and denominator. Okay, so we write out on our second line the cosecant theta times cosecant theta plus cotangent theta. It's a similar solution for the similar approach as we use with the secant theta. So we have cosecant theta plus cotangent theta, and numerator and denominator, so it's essentially multiplying by 1. And we have our u du in the numerator and denominator. Unfortunately, we didn't do the full solution of this problem. We left it at this stage. Oops. With that last problem, we had equals a cosecant squared theta plus cosecant theta cotangent theta, and that's over cotangent theta plus cosecant theta plus AU, and U was secant theta plus C. Now, when we have cotangent, let's write out the derivative of, let's see, we're going get rid of this business. And we're going to now write out y. Let's make it a u substitution. U equals cotangent theta plus cosecant theta du. So cotangent is cosine theta on sine theta, and that's equal to minus sine theta over sine theta minus sine squared theta cosine squared theta. So that's equal to minus 1 minus cotangent theta. And we also have cosecant theta. Cosecant theta is equal to 1 over sine theta, and that's equal to minus sine theta over let's see, minus, let's be careful here. Theta cosecant theta. So this is equal to minus cosecant theta plus cotangent theta d theta. And let's erase our mess over here. And gotta try to keep the board as clean as possible so you can see. And so we end up with minus line, whoops, let's get rid of that, minus a ln cosecant theta plus cotangent theta plus a secant theta plus c. Now we go back and we use our trigonometric association here. We did a trig sub, so we have to convert back to x, and when we do so, cosecant is theta equals x squared plus a squared over x, and cotangent is theta equals a over x, and secant theta is x squared plus a squared over a. So now we have minus a ln x squared plus a squared over x plus a over x plus, now we have secant, so the a's cancel, and we have x squared plus a squared plus c, and that's our final answer. 2 x squared plus a squared on x dx. So now we have our final solution for that. And we can correct our videos.